intelligence, for me, collective intelligence is just a particular state of the system, which is characterized by agents benefit from being in a collective. So imagine, so for me, the collective intelligence is intelligent if the individuals in the collective benefit more than being on their own, not being in the collective, effectively. And as soon as the circumstances changes, this intelligence could easily be converted to collective stupidity and maladaptive pattern, and then being in the group is not beneficial anymore, and being in your own is better basically for the individual. And I think this actually this is the underlying pattern that we try to study in science of intelligence cluster. What are those trade-offs that make, in some circumstances, in some environmental conditions, in some social interaction structure, collective intelligence, and what changes when and how those trade-offs could affect the transition from collective intelligence to collective stupidity and things like that. And I think this is very interesting to study, to understand on one hand, but it's also crucial for us humans living in this age where our social interaction pattern changes so dramatically. We transition from like in the new era of social network, our environment where we live changes dramatically, and this all affects the patterns of our interaction, and then we study those trade-offs in robots, in animals, in humans participating in more traditional tasks like ice fishing. But the ultimate goal is to understand what are those trade-offs that shape the system, and what are those trade-offs that make system intelligent or not.
All right, I'm not sure if I'm jumping already into the hard questions, but maybe a question that I have is, what's then the difference between, say, an organization or just an accidental group or an accidental collective as compared to a collective that's intelligent, or an organization that's intelligent, one that you would say is actually, worthy of being studied because actually it's exhibiting some kind of intelligent behavior? Is there a principled way that we can distinguish between mere aggregates or organizations, groupings of intelligent entities perhaps, and the kinds of things we want to study? We'll start with you.
It's a very good question, I think, because coming from physics, one very simple system to think about is just a collection of magnets, where at one, you could perturb one magnet on one side, and then this pattern goes over the whole table to the other magnets. Would this system be called intelligent? Well, it seems to process some information. So, yeah, that's an interesting aspect of the system. And I think it's also worthy to study that aspect of the system. But I think what would make it actually intelligent is for this behavior also to have some function. And that's where the table full of magnets is different from the 10 thousands of fish that use this behavior to deter a predator.
Yeah, so first of all, I think to make a kind of system intelligence, or some common thing between this complex system is that they actually have specific structure that helps the individual agents to interact with each other, and meanwhile they process the information, and the information could pass throughout the flock. And second, the overall group level, they can self-organize and emerge the behavior that you cannot observe in single agent, or they can solve or finish some specific tasks. For example, the phrase that has been showed by Selina, they stay together and they stay a collective so that they can escape the marine together to increase the lifespan of the group level. So actually they benefit from something from the group level.
So I think maybe we can look at the pattern of certain nature which are not as established as a school of fish, but it's patterns where we look at, for example, hyenas in savanna or some species of baboons in also, which do not live in the collectives all the time. So when you look at ants, it seems like this collective intelligence is really inherent and frozen. But in some collectives, they do not live in groups all the time, but they decide to join the group when it's beneficial. For example, in case of hyenas, when they want to hunt a very large prey, they join in a collective of 40 individuals, and then they hunt this prey, they benefit from this prey, and then they go their ways, and the individuals hunt for smaller prey individually, basically. So it's called fission fusion dynamics, where individuals occasionally join others, and that's also observed in ice fishers, for example, where people might join others occasionally when they think that others are doing better in that particular area, but then when they see that it's not beneficial for them to stay with others anymore, they might leave. So I think collective intelligence is something that emerges. It could emerge in the evolutionary time scale, but it could also emerge on the time scale of actually minutes or hours of particular interaction. Something that could be learned within the life of individual, and for humans, definitely something that could emerge spontaneously for a short time and then disappear as soon as circumstances has changed and it's not useful anymore.
Yeah, so I think that collective intelligence surely should have like a certain role. So as Yunus mentioned, it should have a function. And on top of what Valery said, yeah, sometimes it's actually not clear whether they're doing something really intelligent. Like, for example, in case of the marlins, as I was showing, so we are still not sure whether they're cooperating. They're, of course, competing, because, I mean, everyone is hungry, they want to eat, and there are so many of them, like 30, 50 marlins for this nice fish school. And some of them are actually like very far away from it. You might just think, okay, what they are doing. And one of the things might be they might not really explicitly cooperating, so they're just actually competing, but because they have like several constraints, physiological constraints, and also their body motion, it results in certain structures in space. So as you did mention, structure is very important, which then allows them to do something what they might not really realize that they're doing it, but it helps, for example, to keep this prey in place, and then, as I was also mentioning, prey gets exhausted and just gets isolated by itself from the prey school. And sometimes it happens that actually the marlin who did all the work, who was like attacking and attacking and attacking, and there was another one who was just like passively like swimming around. As soon as like he saw that, okay, the fish got isolated, he just goes there and he catches it, and then it's like, it is actually called scrounging behavior. So and then you might think, is this behavior is actually like part of this collective intelligence process, or what is it? Yeah.
Well, then I will get into the hard question then, because we're getting there. What, and this was an audience question as well, what, if we're looking at different kinds of collective intelligence, different systems, what unifies? Is there any unifying common theme, any underlying principle or concept? And we've heard a couple, I think, so far, emergence or self-organization, that unifies all these different instances. The selfish behavior, say, of the marlins, but the more cooperative behavior of the actual fish that they're hunting. I would assume that they're probably cooperating. Is there, what is there, do you have any notion of a kind of common concept or unifying theme? Maybe we'll start with Paulina and we'll walk our way this way back through.
Yeah, so for sure, like for example, in the case of the prey in this case, so they are cooperating. So, and I think, again, what is like common between all these like systems that if you have like a particular number of like thousands of individuals, so all these like the common principles become really very simple, independent of how smart you are. So this is like, for example, as I was showing these like simple rules, like that I try to be close to someone, but at the same time not that close. That I also try to be in consensus, that, for example, in my direction of motion. And it is often like underlying decision-making problem, like which underlies all the systems. They need to make these decisions on their like individual level, like what should I do, but as a result of these decisions, so they should come to sort of a consensus. And we know that sometimes it might be very difficult, especially for the humans, also depending on the topics. So you might have like polarized opinions and so on. Again, so for example, for these two sort of systems like biological lactation, humans are different things because they have like different goals and there are different consequences of the behavior.
So, I think there are two levels to think about this question. So first one, in already mentioned, is coordination that happens on the individual movement level. But also we can think about the functional side of the story, why fish decided to stay in schools. And in science of intelligence cluster especially, we like to talk about this as a trade-offs between being in a collective and being alone. And I think I don't think about collective intelligence in terms of principles behind it, but about the problem that individuals try to solve, environment in which they live, and social interaction structure that they have. And when we look at those axes, we can define certain trade-offs that would shape the behavior and decision for individual to stay in the group and benefit and use somehow this social environment for their benefit potentially, or decide to be alone and stay alone essentially and do their hunt alone. For example, there is a trade-off of being in this school of prey, because on one hand, the chance of being eaten if you're in a school of prey of millions of individuals is very low. But on the other hand, being in this huge school of fish, you attract predators. So when you're small fish somewhere in the ocean, it's very unlikely that you attract 20 marlins. So as soon as this trade-off gets like the weight of like being alone and potentially have a chance of encountering marlin at some point is over. So this kind of trade-offs, they shape the decision on evolutionary time scale. But this could also happen as a learned behavior, and like I told you, on more like when the foraging situation, when you learn that others are doing better and you decide to follow the leader, for example, and things like that. Yeah. So for me, general principles, again, are defined by those axes that define the system, and then individuals look at those trade-offs within those axes, basically.
Yeah, so I think Alina and Valerie has concluded very well. There's not much left for me to say, but I can try to provide some view differently. So for me, the common principles that we can observe from those different systems in nature is that there are so many numbers of birds or fish schools that apparently don't have some commander there. There's no centralized control. So it's all distributed control, and they don't. They somehow communicate with each other, but not directly. Like no one tells who should do what, but they independently decide what themselves should do based on its own perception of the environment or other neighbors do. And so there is some distribution here in the system. And also there are some information passed through according the individuals, but in the group level, they might self-organize or emerge some kind of pattern, or they might emerge some kind of collective behavior, or they might self-organize into different structures, like the ants, they can using their body to form the different lanes of bridge according to the environment to solve the problem that they met. So I would say the common principles is that they all have different distributed interaction rules, different individual level structures, and different types of information that I get. For example, the birds use visual information, and the fish use sensing information. But in the group level, they all can emerge, self-organize into different collective behavior. Yeah. And I think the most beauty of starting this is that you don't know which kind of roles can determine what in the end in the group level that collective behavior is. And that's how we have to investigate. Yeah.
But sometimes there are leaders, right, in the collectives.
Yeah, and
They
some
emerge.
social animals, they might have some
There
leaders.
should be, we would still call those collectives intelligent, even if there are leaders emerge in those. It's just like a centralized to completely decentralized, right? So there's a continuum.
Yeah. So yeah, it's not always centralized. It's not always decentralized, because to perform specific tasks, centralized information sometimes is necessary because they have to cooperate with them to do certain tasks. Yeah. In this case, we need some certain of centralization.
I find it super interesting to think about these common principles, because that's where we can connect different kinds of systems and see potential commonalities between them. And I, like Valeria, also like to think about this on two levels, but my levels are different. So mine would be level of the individual and then level of the collective. And well, there needs to be some way of bridging these scales, right? That could be an individual fish and the swarm of fish, but it could also be an individual neuron and the brain. So how do we get there? And I like to think about the processes that play a role in doing this. So in neurons, there would be some synaptic connection that can be local, that can be further away. So there's some interaction structure. That's also what we find in the fish. In neurons, again, there is some signal or some language in the form of an action potential. So some electric spark being sent around this, along these connections. For the fish, that's them diving down or turning around. And even with these very simple mechanisms, we already get this vast majority of behaviors. So that's what I find so fascinating, to also think about what these simple mechanisms can already do. And maybe also a short comment on this leader versus completely decentralized decision making. One way to think about this would be, where is the information in the system, or the information to react to? And there may be something like a temporary leader, those entities that have this information, unlike the others in the group. And again, this applies to some part of your brain that just saw something and needs to react to it, but also to the fish, where some fish have been attacked and they know we need to do something and the others don't. So these become somewhat, they lead the behavior and the reaction to some mental.
And I guess one of the more powerful tools we have in our arsenal to be able to abstract principles from these systems is to model them and to simulate them, and to, we don't have access to what the fish is thinking or the rules that the fish is following or the sheepdog is following, but we can simulate what we think are the rules that perhaps they are following. So I want to maybe ask our roboticists or computer scientists first, can you tell us maybe a little bit about how you simulate the systems? What do you do when you're simulating herding behavior or ice fishing behavior in humans? And then maybe I'll come back to Eunice if you want to jump in and add how you simulate your fish behavior. We heard a little bit about, Helena, how you do some of the simulations in your research. maybe I'll start with you.
There's common way of investigating the behavior statistics. So, for example, basically we idealize those individual sheep or birds into particles. We assume that they don't have body length, or they might have, and they might have limited visual information or limited capability. And then we create the simple roles between the interaction of the individuals. For example, we normally use alignment, attraction, or repulsion rules between the individuals, and then we simulate them into in computer. And in computer, we can also observe that with different number of the swarms, they might show or demonstrate different flocking, different collective behavior, like swarming, flocking, or schooling. So the idea is to make idealized assumption that the self-prepared particles can somehow resemble the behavior of the animals that we observe in nature.
So the way we use with my collaborators computer simulations to study our questions, we always start with a mechanism. So we have a hypothesis how, let's say, humans process social information and how this benefits them. And then we try to start with a minimal model, minimal setup that we can run in the computer and try to reproduce a pattern. So we try to reproduce certain behavioral pattern based on the minimal assumption. And then we can stumble upon the insight that, let's say, these components of the system are necessary to reproduce certain mechanisms, certain patterns from human data. It's or animal data, or it could be any system actually. So and it could be astronomy or any system really. But the idea is that we try to replicate as closely as possible nature, but then use a minimal assumption to begin with. So we start from very simple model and then increase the complexity as long as we cannot reproduce a pattern that we're interested in. As soon as we reproduce a pattern, we stop and then we analyze the resulting behavior from the model and see if it's actually nicely replicates what we observe in the data. And sometimes the models could be so complicated that we need to use the tools that we use for studying the actual data to study the model. So same way, is this project called like artificial life, where basically you just run very complex simulation on the computer and just look what emerges in those simulations, and then you use the same tools that you use for nature to study what emerges in the computer simulations.
I think that's a very important way to think about modeling. Like, what are the minimal mechanisms that we need to reproduce some behavior so that we can actually learn from it? And in the case of the fish, one decision I had to make, for example, was to not model their movement at all. Unlike Falina, where movement is the key part of the behavior, I think the key part with the fish I studied is actually this spreading of the diving behavior. And that's a very fast process. So that's like 1 second, it goes a few meters. And within that time, the individual movement of the fish doesn't matter too much. So I said, okay, all fish stay in the same spot. And I rather focused on what do they perceive, are the fish in the neighborhood diving down, and what do they do with this information? Like, when do they decide that they should also dive? And these two components were the most important aspects to reproduce this waving behavior. And actually get patterns that look not exactly like in the biological system, but quite close, I would say.
Yeah. Importantly, there is always a gap between our simulation and reality. And swarm robotics is one of the approaches to try to solve this gap, basically, to loop this back to the real world, where we reproduce this like mechanism from our simulation because we cannot implement our models in the humans back, right? So we need some kind of artificial, so that's an idea, right?
Yeah, I actually want to add one point that after we get the agent-based model in the simulation in computer, we also have another simulator in some robotics fields that we have the physical simulator that reembeds the controller and also the sensor, the rule robotics, and then we apply the roles and also the interaction ways, also the information that they can get from one single robot. We try to implement the mechanism in multiple robots in the simulation, and before we apply this to the real world system, even though they might have the reality gap there. So yeah, for example, the noise and also the time delay when we apply to the real system, it's not so, it's intuitive, but it's not so easy to solve.
You can think about simulation as a map. Oh, sorry.
Go.
Yeah. And like we don't want to make the map too detailed, otherwise it's useless, right? So that's basically our approach. So you can make the simulation, you can simulate every bit of information, but then it's useless because it's so complex that you don't understand what's going on.
Yeah, just probably, just to add or to summarize, and also to one of the questions like which I got even to talk about, like how there's fish and humans, and maybe like you need to have more cognitive power and so on there. But modeling is hard. You know, there are much more of these models than we are talking about. So you can have like this vision-based model, which I think was shown in one of the videos. So there you don't have this weird attraction, repulsion, alignment rules. So they just really operate on what you see, and then they navigate like this. Then there are also exist like really cognitive models where they use Bayesian inference that the agents are real cognitive entities, they have their own beliefs, and then from there you can infer which decision I should make in order to move. So then you can also have like beliefs and preferences and opinions, like humans can have all this like complex modeling frameworks. But then at the end, when you like take all of these models, so the result which you get on the collective level is like very similar or the same. They produce like the same patterns more or less. So, or sometimes like some mechanism, like for example, like vision-based plugin, like this one, it can give you rise to new patterns which you don't see, for instance, with these simple rules, attraction, repulsion, and alignment, or which you don't see with this more cognitive mechanism. But in general, they all can produce this collective behavior. And then exactly as a modeler, you need to understand having some certain particular task at hand, like biologists come to you and they tell, like, I saw fishes doing this, I don't know why. So you just need to select which modeling framework you want to use in order that you can explain this phenomena, and then you select it to your needs.
There's so much interesting stuff here. Okay, let's maybe pick up on one thing that I find particularly interesting then. What would a collective be better at, or what would the individual be better at? If you have an intelligent individual versus a dumber individual that is part of a collective, I seem to be getting the sort of feeling that, well, it depends on the task, but also the answer that both the intelligent individual and a dumb individual as part of a collective could complete the same task. Is that really true? What do you think about this idea?
I think there is a classical example of people collectively estimating the weight of the bull. I don't know if you know this story. It was an experiment done in the beginning of, at the end of 19th century, where just random people on the auction or like on markets were asked the weight of the bull, and when they aggregate those results, the average was just a few grams away from the actual weight of the bull. And this is a classical example of collective estimating certain quality. Certain quantity, and then you have really the power of many wrongs, basically. So many wrongs, but then when you aggregate all this information, it essentially just reduces the noise, and you have perfect estimation. But later research showed that you should be really in a specific circumstances. In some scenarios, like cancer, for example, treatment, having the group of experts is actually better.
It's worse.
um, to have the group. So it matters a group. So there's a lot of complexity when we go in a different task. So when you have a simple task where everybody have pretty much the same expertise, it's one thing. The other thing is it's a very specialized task, and you have the expert. So this collective estimation is an example. So where in the case of like estimation of the bool weight, it doesn't matter like how smart or not smart you are. Essentially, every vote, every opinion is fine as long as you have very large number and then the estimation is good. But in the case of when not everybody is an expert, it's a slightly different story.
Which also brings us to something like collective bias, right? We will see this on the large scale. Maybe, I don't know, a bull of a certain pattern has a different, people perceive it differently, and then we would be able to see if the group actually, makes a mistake in this estimation.
Yeah, and then also, it also leads us to this discussion of echo chambers and, on this like social networks where you have this specific subgroups that we assume that everybody get the same information, but then if you have the subgroup of people that receive specific information, the other subgroups that receive different information, then this collective decision making doesn't work anymore. So we need to really study these social structures and how those social structures actually affect the opinion dynamics and this collective estimation. So, but that's it probably.
I would say actually each individual in the environment, in the system, they might have their own opinion, perception, but also they might have their own belief about what they have perceived. So if the wrong guy has perceived a lot of information, but then he has the largest belief, or the larger amount of the people or agents like this, they have very high belief about the wrong information, then they might make the system not work anymore. But it also has been researched that to make a large swarm, that to get the same information in a short time, actually you only need a very small amount of informed agents. So I would say with some informed agent that could help the system to function correctly. It also requires all the other number of uninformed agents to reach the consensus with its neighbors. So it all depends on the belief and also the perception of the informed and uninformed agents.
About this informed and uninformed agents in the group. So I think it's also what is fascinating about it, so that you can have like, it's actually was shown that about 10 agents in the group who are informed about something is enough in order to lead the group. But then there is also this kind of problem, at least in my head, but if these 10 agents are malicious agents, so if someone hacked them and took control and he knows how many you need to hack, and then all the system starts to behave as someone else wants and not actually what it's supposed to do, like how can we protect like this collective system then from not doing this, because we don't want this behavior. So this is, I think, might be like one of these like kind of probably big spots in it, so that these emergent properties, so it's like really then, I don't know, what you guys think, what you would do with this?
I think it just illustrates that collective, like intelligent collective, they are also always on the brink of failure. So as soon as you have, instead of informed individuals that try to lead the collective to a good spot, you have malicious agent. This strategy doesn't work anymore. And if collective is not adapted to this new circumstances, it leads to the disaster, right? And we observe this in birds, for example, that orient by stars, and then as soon as this environment has changed, and they basically just hit the rock or something like that, that they cannot navigate anymore because the environment has changed. So this collective, like intelligent collective, they adapt to certain conditions, and then when conditions have changed, sometimes collectives are not robust, and that's observed in humans, and it's observed in.
I don't know if I would say that collectives are at the brink of failure, like constantly.
Yes.
Because like any system, you can find some parameter that if you increase or decrease it too much, it will fail. If you stop drinking water, it would be a problem. But as collectives can also be incredibly robust, right? Where the individual, well, is not so important for the behavior of the collective. You can even take it out, and that allows the collective still to function in this way. But it's fascinating also what the failure modes are, right? In the case of the birds, for instance, that they are suddenly no longer able to find a target. It can be something seemingly trivial, but it's can become very apparent in these cases.
For my point, I mean, in the robotics field, the malicious robot is really important task that we have to solve, because an intelligent swarm robotic system should be able to identify the malicious robot and to remove it or replace it, or even if it's not malicious at all, it just one robot doesn't work anymore, it just malfunction somehow. And the system should be able to react to this and to remove the robot, or replace the robot, or even repair the robot. So this, I think, is very important aspect for us when we think about how we build an intelligent, robust robotic system.
Maybe one more thought to the malicious agents. I think oftentimes in these examples where a few agents are able to put the collective into a certain direction, we don't assume that the collective can perceive what direction it's going in and what other goals may be. And I think that's one of the ways how a collective can actually steer into another direction if it realizes which way it's going and who the malicious agents are. And in a way you need to have a macroscopic perception of what the collective's doing.
Yeah, and this is what is like very different from the classical terms, right? Because they'll always tell, okay, these agents, they don't know about the global state of the group, but when you want really to engineer the robust system, you need to go away from these classical assumptions. The agents might be not homogeneous, they can be heterogeneous, and actually it's already shown that heterogeneity even like improves the functionality of the collectives in many ways. And then it's also probably how can we make and engineer the agents in a way that they can have this kind of like, probably not consciousness, but they can also realize, what's going on in the whole group, but it's like really hard to do.
So just maybe one example of what you were saying about robustness of the system. In the human society, we have a reputation system, which prevents essentially like malicious agents taking over usually. But again, that assumes certain type of social interaction, and in social media, for example, reputation system would work very different, and it probably doesn't prevent this malicious effect as good as if we live in a small society where we know each other and can trust our reputation beliefs about others. It's just an example. But yes, I think it's
I think on that interesting note, we should open the floor to questions from the audience for all of our panelists or one of our panelists, and I think we have our first question right here.
Absolutely. It's very fortunate to be in a room with the interdisciplinary experience and background, and something that right now in today's society we're approaching AGI in that. So the question right here goes between actually all of you, in that what would you say with emergent phenomenon where you could then classify would be consciousness of a distributed system in that, at what point, where it becomes either mechanistic versus non-mechanistic version and measurement of it?
That's a tough one.
Because we observe these things. Well, I guess the best way is how would you classify in a distributed intelligence system where emergent or that an emergent phenomenon occurs, whether that's conscious or not, in a sense.
I would say somehow the conscious we could define as like flexible, like when the environment changes or when the task changes, the swarm should be able to react to it, to adapt themselves to solve different tasks or to self-adapt them into different patterns according to the change of the environment. Yeah. So.
I think the question is about consciousness, right?
It's a little bit of both. Of how do you take? Would you, when you have, because we exhibit emergent behavior when you put them together. Now, how do you then differentiate when that emergent behavior actually starts going, stepping into the cognitive level, where you actually have a conscious, intelligent, system?
Yeah, I think you need a much tighter coupling between agents in order to such thing to emerge. So if you think about neurons, they went through very long evolutionary history of being like working together and having very tight coupling in order to actually function as a body, right? And produce such a robust emergent phenomena as consciousness, I believe. But
So,
I think this is very tricky question because consciousness itself is very like difficult concept, and we don't really know much about it. So it is fascinating to think about this, but I would say it goes beyond scientific.
well, in a coupled system like that, could that be a collective memory system in that they share?
That's true. That's true. That's definitely true, and I think it's fascinating research.
Yeah, I wonder if it maybe requires this emergent entity to also have a goal or some clear target that it gives to itself in a way. But yeah, that's really mostly an intuition on my side. I think consciousness as a term is very loaded also. If we think about an ant colony, we don't perceive it as, we don't think about it as conscious usually. Most people maybe correct me if you think differently. But what doesn't make them conscious, right? They have a goal, they are huge collective, and yeah, maybe in the same way when thinking about AI systems, we are moving the goalpost of saying, okay, yeah, this is not yet conscious, whatever that is. But maybe it's a point to reflect how we understand the term, and if it's not more a term that we use to describe ourselves, to understand ourselves better.
Well, what about the philosophical, in there?
Just maybe a last comment. So here is maybe we should think about not in terms of consciousness, but in terms of culture, because culture is something that is also emergent out of the interaction between individuals, and something that observed in animals, but also in non in humans.
I think we have a question here, and then we'll go back there.
I'll tone it down from consciousness to emergence itself, which is also a difficult topic. I mean, historically there's something special about emergence, but in your field, do you actually see it as anything special? I mean, it's considered a separate layer of existence with its own rules, but is it actually anything special other than just running these rules?
I think, or at least for me, it's surprising how simple these microscopic rules need to be to already show something like emergent behavior. So I think that will always make it special to me in a way.
But when we say emergence, we think of something, a new level of science operating that has its own rules, that is not dependent per se on the components. And that's what historically works. And it implies something like maybe in collective intelligence here that it doesn't apply, but there's just larger perspectives. I mean, can you mathematically define when a system is emergent? Is there some new information? Is there, et cetera? Like what sort of metrics do you use to say this system is emergent? Simple rules generating interesting behavior is not special. Right? This is well known. So, but we've heard the term emergence a lot today.
Yeah, but maybe if at this collective level, it also produces not only a complex pattern, but actually a function that's useful for the collective. That is my working term for emergent behavior. How would you describe it?
I would Yeah, in statistics, we have some definition to describe where the system behaves in the emergent level. For example, for the alignment behavior that we have seen in flocking, in birds flocking, we use the polarization. And we also, for the fish mating behavior, we use angular momentum to define the level of the extent that how the system emerged in a collective behavior. And also, when the system arrives at a certain kind of consensus, we can observe some other properties, like they might have shown specific type of transition, this concepts in statistics, and or they might show some specific property like scale-free, like you can observe the information passed in rather short time in the large swarms. So this is kind of interesting perspective that we observe from this system when it reached at equilibrium state.
I personally don't think my personal opinion is that there is no special about emergence. So I think if we observe some system level properties that basically go beyond individual, beyond just a simple sum of individual agents, basically individual parts of the system, that could be called emergence in not so interesting cases you point out where it's just a simple interaction rules lead to an interesting pattern. I would call this emergence as well. It's just a working term for something that we do not understand very well, maybe yet, or something that we could not potentially understand it because it's so complex that like those rules, we don't grasp those rules exactly at the moment, so we call this emergence. But I think as soon as we can define this mechanism and build this link mechanistically, we don't need this term anymore, essentially. That's my position. But I think this is more of a philosophical question. If you
In the extreme case, emergence is there's information flowing between the levels, right? So
Yeah.
the behavior of the collective actually influences the way the individuals behave, right?
Yeah.
That's the extreme version. I don't, except for turbulence, I don't think that's been seen anywhere.
Yeah, I agree with what was said, and for me also emergence is mainly in case of the biological system that you see an emergent benefit. So because it might be an individual rule which applies, but for example with this like thin angle, the agent like escapes alone. They also do it alone. They escape like at certain angles and so on. But then there you don't have this another, for example, metric which you have in a collective, this like recovery time, which means like splitting time, because you want to be in the collective to have this protection power. And then you can interestingly find out that these certain rules basically you didn't encode them to do that. Like basically it's encoded to maintain the distance, but as a byproduct it also allows like very quickly to reorganize back to be together. And this is what I wasn't like put it in the model originally, and this is what appears, which serves a function, because then they not only like go away, but also they quickly come back together.
I actually want to add one point. The emergence, somehow we call it like transition, actually happens in a very short time, and also happens when we observe the group state change. For example, in the fish schools in the United States, the fish might dive in under the surface or above the surface. There are different states between them, and the emergence happens while all of the agents, all of the fish, they transform into one state. So that happens in a very short time, especially when the birds come in. Yeah.
There's a question here and then in front.
Yeah, thanks for the discussion. My question is how you draw boundaries between collectives, because I mean you can scale up infinitely basically, and then I mean is it a matter of the researcher's taste to draw boundaries between collectives, or are there certain criteria that could help to decide where a collective ends and another begins?
Could you clarify maybe the question?
Is it about the size strictly?
Yeah, like I mean, like in your case, like is the collective the fish school plus the marlins, or just the fish school, or is it the whole ecosystem of the ocean that is a collective, that, and then be a bureau of collective intelligence? So
I think this is also like something like it's having more actually better or like something like this. But I think it also then highly depends on the system. Like for example, when you have like two collectives, like in that case with the hunting system with the marlins, so you need to look at them like differently. So for the prey, it's better to have the more the better, like 10,000s, even like great or billions, because then it's like such a huge, massive bait balls, we biologists call it like this, of fish that the predators even like, they cannot do anything. They cannot really like even strike through it because it's so dense and it's also so confusing. So they cannot attack at all. But what they do actually, they try to break this school to smaller sizes, these manageable ones, as I was showing, which are much smaller, and then you can see all these fountains and so on. But in these huge ones, there is nothing. They're like really very safe. But for example, for predators, there is actually a certain limit, certain number, which basically then is beneficial. And then after this, they become redundant. So it also, again, highly depends on the function for what they do it, and on their own characteristics.
And I think the question is very interesting, and I think we definitely could think about the ecosystem as an intelligent interaction. The point is that like, the way we define the intelligence, collective intelligence, as something that happens in the collective that benefits individual in the collective. So when you include marlins and their prey in the collective, it's a complex system, but you have two intelligent collectives. So I wouldn't like increase this term to the whole ecosystem only to a collective that actually have the same task to solve, basically. If you have a contradictory task, that's two different collectives, basically. So you can think functionally.
Yeah, so maybe choosing a classification that helps the question that you're going to answer. I don't know, our bodies are billions of cells, right? We can look at these cells as one thing, which is often useful. But we can also say, okay, there are some cells that form an organ, and as this group of cells, they have a certain function. So yeah, it depends a lot on the layer you are focusing on.
I think we had a question in front, and then we'll go back.
Yeah, the reputation crisis of elected governments led to the idea of supplementing them by collective intelligence of citizen groups, so data. Is there research if this could work, how fragile it would be, how it should be done?
There's definitely research about that, but I don't think anybody in this panel is an expert on this, unfortunately.
But from the research we do, maybe some statements can be made, but careful statements. So I would say the clear benefit of such a group is that it removes some sort of bias that an individual will always have. But if you select these people randomly, one clear benefit would be that they ideally don't have such a bias and no self-interest that they can propel. So that would be a statement I feel comfortable with, even with my research. But I'm sure there's more in depth on this, and also some practical examples from France, I believe. And then,
Anyone want to weigh in on that question?
So on that, when you, as you were saying right there a second ago, where you have your atom, your molecule, your cell, in that, your hierarchy in that, how is it that or what examples in biology per se have you seen hierarchical organization, and then how would they learn and then optimize their learning over that into the hierarchical groupings of that in systems? So how do, in a sense, the learning, because much so the way that our brain does is that we start grouping things hierarchically. How do we optimize that mechanistically per se in that? And what do you guys know of any existing systems, like biologically, where they exhibit, this type of behavior.
So, well, this goes away from collective intelligence quite a bit, but it's super interesting how these hierarchies.
Well, in a distributed, like, if we separate them out, where each atom is a separate entity, in that where they then are learning together, where they then start grouping, say just like you would have an organization or a company, where each individual people start organizing into groups, and then how do you optimize, the information transfer amongst them into being intelligent and operating as a collective intelligence in that manner?
I think one way that this was solved in nature of this evolution, right? We are the product of billions of years of evolution, and evolution seems to be able to generate hierarchically structured systems, starting from very simple cells to more complex cells, multicellular organisms, collectives. There you have this hierarchical structuring already appearing, but in a way it's an optimization process over long time scales, and depending on the level you're looking at. I don't know if this answers the question, but I think evolution is very important in finding what the modules could be and how they communicate, and when it makes sense to group them into a new module, right, for example.
Would you know of a mechanistic way to actually, test that, like in simulation? Or how would someone take, that exact idea right there and actually put a mechanistic version of it?
I think what Valerie also mentioned is this artificial life project or community. They are trying to do this from very first principles. So, question being, how complex substrate do you need to generate, to allow evolutionary processes and to allow them to generate something, larger and still being able to continue doing this. So that might be the direction.
Well, that's awesome. Appreciate it.
Is there
Yeah, for sure. Information, theory network there.
okay? Question, and then last one in the front here.
I have a question on how, or possibly what the current state is of finding like a generalized model for collective intelligence. So you mentioned like a catch-all term for rating collective intelligence, which would be emergent benefits. If we, I don't know, fix it to something slightly more concrete, like the survivability of a population, is there something like finding a simulation in context A, combining it with a simulation in context B, and then maybe not entirely solving the simulation in context Z, but at least getting to, or having like a head start. So is there maybe like higher level, patterns that aren't human intuitive, but that could form like a rich substrate for, in general, collective intelligence?
I think it's a very difficult project because each collective solves very different problems. So we mentioned multiple things today. For example, some animals try to forage and find a good spot to eat. Some animals try to survive at the attack. Some animals try to, other way around, attack the group. So I don't know. So we can cluster those collectives by tasks they are solving, and then derive certain general principles, and that's what is done in the literature. For example, but then if you think about like fish and birds, they have very different modes of locomotion, and then are those rules that apply to fish would also work for bird? I'm not so sure, and that's I think the very tricky question. If we even want to arrive to this quintessence of collective intelligence, doesn't even exist. So my argument is collective intelligence is circumstantial, and it crucially depends on the environment and the task that individuals are solving. But what were other
Yeah, I agree with Valerie. So it kind of depends on the system which you study, because each different system has their own constraints. And actually constraints, they also define what you get as a divergent phenomena. Because for instance, fish has lateral line, birds don't have lateral line. for birds, it's like they cannot collide at all. It's like very deadly for them. Fish can like really swim super close, like almost touching each other. And I mean, but also like tiny things which one might think they make huge difference then on this collective level. So that's why, yeah, it would be very hard to generalize it. But actually, it's a dream, I think, of the theoreticians to get such a dream model which will describe the universe and everything. Yeah.
Yeah, I think it's actually the nice way to see the universe or generalize saying of all these different complex systems. I could provide something similar, try to define this. I think the complex system is made of different, for example, large amounts of components, and each component they have different and or limited individual intelligence. In the sense, like with Paninaceae, like the birds might have higher velocity, and the fish might have different way of moving, swimming. And for ants, they don't directly communicate with each other. They only indirectly communicate with each other by the pheromone. So each component they might have limited individual intelligence, but we can define this as kind of agent or component. And all of these component agents, they can cluster or function together, and then they can self-organize and emerge in the group level in different functions or different collective behavior. It's really depends. I mean, the function or the behavior, the patterns that we observe in different complex systems really depends on the individual intelligence of those components or agents.
Then one last short-ish question if there is.
So, emergent properties can also be seen in AI, especially the transformers model, so which is like an AI trend. So can emergent properties be considered sign of higher intelligence or creativity, or is it just a function of individuals coming together?
I mean, you can observe emergent properties in just chemical like elements put together, right? But there's no intelligence in the fact of property being emergent, right? So in physics, there are plenty of examples where you observe such inert, like magnets, for example, where you see this. So I don't think the short answer. I don't think this is the case. Any other panelists? A short-ish answer.
Not for me. I agree. I think with that then, please join me in thanking our panelists.